If you're a developer, you've probably typed git commit thousands of times. It's just muscle memory at this point, right? But have you ever stopped to wonder what's actually going on under the hood when you hit enter? We're going to peel back the curtain and see how your entire project history is built into this brilliant, tamper-proof structure. So that's the big question for today. What is really inside a Git commit? You know, on the surface, it feels like just saving a file, but it's so much more than that. And by the time we're done here, you'll see the elegant design that makes Git so mind-blowingly fast and reliable. Because a commit isn't just a save point. Every single time you make one, you're forging another link in a permanent, verifiable chain of your project's history. And to really get how that works, we got to take a quick trip back to see where Git even came from. So, picture this. It's 2005. Linus Torvalds is wrangling the absolutely massive Linux kernel project, and he's got a major headache. He needs a version control system that can do three things perfectly. 1, it has to be blazing fast. 2, it has to work for thousands of developers all over the world. And 3, the big one, the integrity of the code had to be completely unquestionable. The system he built to solve these problems is exactly why Git works the way it does today. The easiest way to wrap your head around Git's internal database is to think of it like 4 simple types of Lego blocks. These are the fundamental pieces, the core objects, that everything else is built from. So let's meet our 4 builders. First up, we have the blob, and it's pretty much what it sounds like. It is just a dumb chunk of data. It holds the raw contents of a file and nothing else. No file name, no permissions, no timestamps, literally just the bytes. Every unique version of a file in your entire project gets stored as one of these blobs. Okay, next is the tree. A tree object is basically a directory listing. Now, it doesn't actually contain the files. Instead, it holds pointers. It'll have a pointer to a blob for each file, and this is key, it'll point to other tree objects for all the subdirectories. This is how Git maps out your entire folder structure. And now for the main event, the commit object itself. A commit is basically a snapshot of your entire project at a single point in time. It does this by pointing to the top-level tree for your project's root directory. But here's the magic trick. It also points back to its parent commit, or sometimes multiple parents. That's what creates the chain of history. And of course, this is where all your metadata lives, the author, the timestamp, and that all-important commit message. And our final Lego block is the tag. This one's super straightforward. It's just a friendly, human-readable pointer to a specific commit. Think of it like putting a permanent sticky note on a version you care about, like v1.0, so you can always find it again without having to remember some crazy long hash. So let's see how they all snap together. You start with a commit. That commit points to one top-level tree. That tree then points to your files as blobs and your subdirectories as other trees. It's this simple hierarchy that allows a single commit to represent the entire state of your project at that moment. Pretty clever, right? Okay, we've got the blocks. But what's the glue that holds them all together and gives us that unquestionable integrity Linus was so focused on? Well, it all comes down to a clever use of cryptographic hashing, which creates this incredible, unbreakable chain of history. And here is the absolute key to everything. Every single object inside Git, whether it's a blob, a tree, or a commit, isn't identified by a name, but by a unique ID. And that ID is a SHA-1 hash that's calculated from the object's content plus a small header. This is what it means when people say Git is a content-addressed file system. The content is the address. Let's make that real for a second. If you take the simple string hello world and run it through Git's hashing logic, you get this exact 40-character hash. It's completely deterministic. The same content will always produce the same hash. But now, watch this. This is where the magic happens. We change one single character. We just capitalize the H. Look at that hash now. It is completely, wildly different. There's no resemblance at all. This is a property of good cryptographic hashes called the avalanche effect, and it is the bedrock of Git's data integrity. So this creates this amazing ripple effect. If you change even one byte in one file, the blob for that file gets a totally new hash. Now, since the tree that points to that blob now has new content, the new hash, the tree gets a new hash. And then, since the commit points to that tree, the commit gets a new hash too. The takeaway here is huge. You cannot silently change history in Git. It's impossible. You don't edit old commits, you only ever create new ones. So with every commit pointing to its parent, we get this beautiful chain of history stretching all the way back to the beginning. But let's be honest, development is never a straight line, is it? You have features, you have bug fixes, and that's where the true genius of Git's data model shines. It's not just a line, it's a special kind of graph. And knowing this helps us bust a couple of really common myths about Git. Myth number 1, Git stores changes as diffs. Nope. Git stores full snapshots of your project. It's incredibly efficient at it, but it's always the full picture. Diffs are just calculated on the fly when you ask for them. And myth number 2, a branch is like a folder that contains commits. Not at all. A branch is nothing more than a simple, lightweight pointer to a single commit. That's it. So this brings us to a really crucial idea. A commit can have more than one parent. And anytime you see that, boom, you're looking at a merge commit. This is the feature that turns a simple timeline into what's called a directed acyclic graph, or a DAG. It's how Git masterfully handles all the complexity of parallel development happening on tons of different branches at the same time. Okay, that was a lot of theory. But let's land the plane here. Why should you care about any of this? Because this elegant internal model is the direct reason why Git gives us that incredible speed, ironclad integrity, and amazing flexibility that we all rely on every single day. This right here brings it all together. Think about it. Making a commit is fast because Git only has to write new objects for what changed. It reuses everything else. Branching is literally instantaneous because all you're doing is creating a tiny file with a hash in it. And even complex stuff like diffing and merging are super efficient because all Git has to do is walk this really well-structured graph. It's all connected. So if you remember just 4 things from this, let it be these. 1, Git is content addressed. The content defines the ID. 2, its history is immutable. It's a tamper-proof graph. 3, it works with snapshots, not diffs, which is a secret to its speed. And 4, branches and tags are just tiny, cheap pointers. So go ahead, make branches for everything. They cost almost nothing. And I'll leave you with one final thought to chew on. We've just spent all this time establishing that Git's history is immutable, right? So when you run a command like rebase and someone talks about rewriting history, what's really going on? Well, think about it now. You're not actually changing the old commits. You're creating brand new commits that are similar and then just moving the branch pointer over to your new shiny timeline. The old one is still there, just waiting to be forgotten. It's a whole new history built on these same powerful ideas.